All right, so continuing chapter 20, I want to talk about a little bit of how, with a galvanic cell, how do we know who is going to be oxidized, who's going to be reduced? Because again, in a redox reaction, somebody's always losing, somebody's always gaining electrons. How do we know that? So you need to have your reduction potential printed out for you to kind of understand this. So this was a table that they used to give on the AP test for you to use. And realize that this is under what we call standard conditions of 25 degrees Celsius, like everything else we've seen with the last chapter with thermo as well. So up here on the top is F2 plus 2 electrons goes to F minus. So realize these are all half reactions and they're all reduction potentials, meaning these are all reduction reactions. So you will see the electrons are always on the left-hand side. Now this E0 is called the cell potential. We'll talk about that in a little bit. But for right now, I just want you to look at the reactions themselves. And again, this is just a general table they put together for the AP test. There's more extensive ones out there. But for F2, please write down most easily reduced. So if you think of fluorine, it wants electrons, okay, to complete that octet. So it really wants to take on those two electrons. Well, if you go to the bottom of the table, something like lithium or any of these metals, they don't want to gain electrons. They actually want to lose. So write down least likely to reduce, least likely to reduce. So the further you are up on this table, the more likely you are to reduce. The further down you are, the more likely you are to oxidize. So if we go back to our reaction here, I have zinc and I have copper plus 2. So realize with copper, it is a little more tricky because you do have to look at what copper you're talking about. So if you go to a third way down, copper 2 plus 2 electrons goes to copper metal is 0.34, and we'll come back to that number a little bit later on. And then if you go down and find zinc, that is 2 plus 2 electrons goes to zinc is negative 0.76. So that means the copper wants to reduce and the zinc wants to oxidize if you're comparing those two. The further you are up on the list is going to be the one that reduces. The one that is further down the list is going to be the one that is oxidized. So that is why this does what it does, is because of, again, this is what nature has given us. Well, where do these numbers come from? Well, to kind of give you some background, if you flip to your next page of your notes, you will see another diagram here. And this diagram is focusing more on where do we get these numbers, okay? And these numbers are due to each half reaction. So how do I know in terms of voltage, which we'll talk more about, how do I know what I have there? So what this is a basic setup, and cross out this reaction down here because it's not correct. So over here you have a piece of zinc in a zinc solution, and it is connected again to a voltmeter. You have a salt bridge, it's a different salt bridge for this one. But over here you have a piece of platinum or some inert metal in a glass tube. So this is a glass tube. And what you have is hydrogen gas pumping in. And this is a setup for, if you look at your reduction potentials, some of them are gases. So how do you actually do a cell like that? Well, you have to pump the gas in through the solution. So you usually have some kind of glass tube for that. So hydrogen gas is coming in here, and H+, so I must have some acidic solution in here, okay? And you need to have some kind of metal in order for you to transfer electrons, by the way. So that's why it needs to be a metal. So this is what we call a She, the standard hydrogen electrode. So this is the hydrogen end, this is the zinc end. So the hydrogen end gives no what we call voltage. So that means whatever I get in terms of the voltmeter is due to just one of the half reactions, whatever is in this cell over here. So for example, if zinc is becoming zinc 2 plus and giving off 2 electrons, this other cell is 2H plus 2 electrons goes to H2 gas. And when I look at these two reactions, I then add them up. Zinc plus 2H plus aqueous goes to zinc 2 plus plus H2 gas. So this is how we know, if we look at the table, okay, if we look at the table, that zinc is negative 0.76, because again, zinc is becoming zinc ion, and on the table, it's the other way around. So we're going to talk about charge here in a second as well. But when we're doing these half cells, okay, there is another notation that we're going to use called line notation. And this is to show the cell itself without having to do a lot of drawing. So sometimes you're going to see a full setup where you're going to see two cells and the metals and all that. Well, line notation is a much shorter way of doing it. So you are going to see it written this way. So give me a moment and I will show you the set. All right, so salt bridges, excuse me, line notation, and I'm going to show you a couple examples here, are always going to be in the same format. That's the good news. So on the left-hand side, you're going to write the metals symbol. You're going to draw a line, and then you're going to write the ion symbol. Metal is going to be a solid, ion is going to be aqueous. You're going to draw two vertical lines to indicate you have a salt bridge. Then you're going to draw the ion symbol, and then the metal over here, and you're going to draw a line between the two. On the left-hand side will always be your components in your anode, where oxidation is taking place, where you have a loss of electrons. And on the right is always going to be the cathode. So that's always going to be where reduction is taking place and you are gaining electrons. So let me show you with an example. It'll make a lot more sense. So please go back to your Daniell cell, your zinc and your copper combination. So we will always have the anode listed first and then the cathode listed second. So the anode is where you're going from zinc to zinc ion. So I'm going to write zinc solid, a vertical line, then zinc ion aqueous, two double lines. Then I'm going to go ion, which is the copper 2 plus aqueous, a line, copper solid. Okay, so that is the line notation for this cell. So if you were to write this down, any chemist would know exactly what you have set up for your galvanic cell. Okay. All right, let's go back to the other one, okay? So I have zinc plus H plus going to zinc 2 plus and H2. So for this setup, the zinc is undergoing oxidation, okay? It's losing 2 electrons. So I have zinc solid plus zinc aqueous 2 plus, double vertical lines. Then I have 2H plus aqueous, a single line, and then H2 gas. All right, so reason I'm doing this example is I need to have a solid on both sides. Okay, I need to have a solid on both sides for the line notation. Mainly because for the setup, I need a metal in there in order for me to transfer electrons. That is why metals are so helpful in the fact that they transfer electrons very easily. So in this line notation, because I'm using an inert metal, I need to include that in my line notation. So what you will sometimes see if there's a gas or if both of these are aqueous, and you'll see a couple examples of that as we go forward, you always draw an extra line and then write down PT solid. And platinum can be your go-to for any metal that you need, but it could be any inert metal that does not react in that situation. So this is again called line notation, and it's a nice easy way of writing a galvanic cell without drawing the whole